So today we're going to talk about tangents and limits. We talked about tangents already because we talked about how you could use the tangent line approximation to estimate what a small change in x does to the value of a function or the y value. And that's how calculus works, is by using changes, studying changes to make models. We didn't have a good way to get the actual equation of that tangent line. And so we were just eyeballing the slope. We knew a point and we eyeballed the slope. So today we're going to be much more precise. And what we're going to do is do that using limits. Now, why do you care about limits? You don't. You care about one particular limit, and I'm going to write it down for you here. And there's a couple of changes. This is something that you're used to and something that you're not used to. So let me kind of walk you through what I've got here. This is the expression. Now, if you get rid of the new stuff, you recognize this as the average rate of change of the function f, change in y, the difference of the f values, and over the change in x. That's the average rate of change, or the slope of the secant line. The new situation here is that we put in these symbols in front. LIM is just short for limit. You just can't do anything about it. And then over here in red is something that I'd like to make a little controversial. I say that means that h is near 0. And a lot of people say h goes to 0, but that's wrong. H isn't going anywhere. H is near 0. So we want to worry about this particular limit, and because that's going to tell us the exact slope of the tangent line. Okay, let me give you a couple of simple limits just to kind of show you why you don't care. And so the first one I'm going to write down here is, these are silly. If x is near 3, well, that means that x plus 2 is near 5. I don't think there's a big mystery about that. And you can play with that with calculators or numbers or something. But this is pretty straightforward. And that's why I like to say that h is near 0. If x is near 3, x plus 2 is near 5. And if x is near 3, then 3 times x is near 9. And a lot of people have gone to a lot of effort to convince you that that's true, but it seems kind of self-serving to me. The problem with this is that it's not so straightforward, because at the top here, well, at the bottom's a little bit easier. The bottom's near 0. That's how I got this scar in 8th grade. The top, if you think a small change in x is going to lead to a small change in y, the top is near 0. And so that's the situation that is trickiest and most important for us in calculus. And so there's only one way around this, which is to do a lot of algebra. So I'm going to do one example, and it's the standard first example. So I'm writing it out here, and then I'll walk you through it. So I'm going to use the squaring function, f of x equals x squared, and I'm going to take, if I cover that up, there's the average rate of change, and so that's a fraction. The bottom is h, the top is the difference between two squares, x plus h squared and x squared. But now we want to take the limit, see what happens when h is near 0. H is near 0. H is not 0. Can't be, it's on the bottom. But h is near 0. And so we just have to do some algebra here. I try not to do too much algebra, but sometimes you just got to. So one thing is, do the parentheses first, and then the square of x plus h is x squared plus 2xh plus h squared. So that's just the standard squaring. I'm still worried about what the limit's going to be, so I'm still going to say I'm doing that. And I'm going to continue by simplifying the top of that fraction. This really is simplification because, and this happens in all of these, is if you look over here, you've got an x squared minus x squared, so those cancel. So we're going to cancel those out, and now what's left on top is much simpler. It really is simplifying. It's not just some arbitrary math teacher thing. What's left on top is 2xh plus h squared, and there's a common factor of h in there, and so we'll take that out, and something wonderful is going to happen. We're still doing limit for h near 0. The bottom is h, and the top now is a product, h times 2x plus h. So I've used the distributive law to take that out, and the h's cancel. And so we're left with the limit for for h near 0 of 2x plus h. Well, if h is near 0, 2x plus h is near 2x. And we have now done this limit. This is the hardest limit that you have to do in Math 160. So, okay, we got it over with. And let me remind you of what's going on here geometrically. There's a reason we need to do this. And next time we're going to go through a couple of these just so that we get standards for the elementary functions. But the situation we're going to be in is this. We have a graph of some function, y equals f of x. Nothing unusual there. And we're going to pick a point that we're interested in. And so I'll call that point x. That's the x value. And the y value is f of x. That's what puts it on the graph. And then we're going to have a secant line. And so I've drawn in the secant line. And now we have the coordinates at the other end, the other place where the secant line cuts the curve. Remember, secant is just Latin for cuts. Tangent is Latin for touches. Secant is Latin for cuts. So anyway, the points here are x plus h and f of x plus h. Make sure you shifted it over, right? So you want to add h to x and then evaluate the function. And the slope of that is the what I just wrote down. So we have, it's a fraction, it's a slope. The bottom is h, that's the change in x. And the top is the difference in the y coordinates. One of them is f of x plus h, the other is f of x. So that's the same old rate of change, slope of the secant that you'd already done. And the big difference here is we're going to take the limit for h near 0. H doesn't go to 0, h is near 0. If you keep thinking that h goes to 0, it's going to really mess you up. It's been messing people up literally for 350 years. H is not going anywhere, h is near 0. If h is near 0, x plus h is near x, and so forth and so on. Anyway, so this is the slope of the tangent, and if we do a little bit of algebra, we can make this into something useful and solve a bunch of problems, make a bunch of models. So that's what we're aiming at. That's the one limit that you care about. All the other stuff is for math majors. No more need be said. So look at the WebAssign stuff and also read my thing. It's called Intuitive Limits, and it's on Moodle, and that goes into some more detail about this. So, or rewind this. Ask me questions on the forums, send me email, keep in touch, and talk to you soon.